Hello? Hello? Okay. Okay, I see. Thank you. So today, in the first lecture, we are going to focus on causal representation learning. Actually, you can consider causal representation learning as a kind of broad problem of causal discovery. You still try to, try to discover the underlying causal structure together with a lot of latent variables or hidden variables, right? Remember, in the world, there could be so many hidden variables. And understanding hidden variables can really make us totally different because we can really try to see how to make use of them, and our world will be more resourceful. So as a consequence, I will first finish the lecture on causal discovery, focusing on some emerging results, and then we'll focus on causal representation learning, which mainly focuses on latent variables. Okay. So right here, yesterday we were here. GS. Okay, we know why we have to use two steps. We go forward to add edges, and then we go backward to remove edges. Now, faithfulness is a fundamental assumption underlying traditional causal discovery method. Right? What's faithfulness? Basically, consider this example. This is a health condition, the mortality risk. This is a healthy lifestyle. So suppose now you can see there are two ways for health condition to influence mortality risk. And if A equals minus BC, right here, then you can see the influence from health condition to mortality risk will disappear because A plus BC is 0, right? This guy does not, in fact, this guy does not receive any influence from this guy. As a consequence, although X has an influence on Y, they are independent. So this is a violation of faithfulness because faithfulness says there are no accidental or fake or spurious independence or conditional independent relationship. Now this is a violation. So this is a typical scenario where faithfulness is violated. First of all, the chance for this faithfulness assumption to be violated is very slim. Why? Because we know modularity. There are different modules. Parameters are chosen independently, right? They are not coupled. As a consequence, the chance for this equality to hold true would be very slim, right? With measure 0. That's why, generally speaking, faithfulness assumption shouldn't be violated. However, if it's violated, then classical methods, including PC, FCI, and GS, may get into trouble. Why? Because if they are independent, then we say there are no link in between, right? There are no link in between. That's wrong. However, now I'm going to talk about another method. In that method, we don't need faithfulness at all. So, however, at the same time, we need to make some other assumptions. Remember, assumptions are always needed in learning because you are doing induction. Whenever you do induction, you need assumptions. Even if you want to make prediction, you have to assume that the future data will follow the same distribution, right? There are so many assumptions. Now, let's see how we can derive the emerging approach to causal discovery. Let's look at those scatter plots. So these are known as the Tübingen causal effect pairs. So we are given the values for x1, x2 in the first one, second one, and so on. And then we are asked to figure out which one is the cause and which one is the effect. We don't have time information, right? We don't know which one is happened first. We have no idea. Now, how can we figure out which one is the cause and which one is the effect? Do you think it's possible? You are given two variables without any time information. Can you figure out which one is the cause and which one is the effect? Actually, the answer, sorry? Do you think it's possible? Just forget about the method. Do you think that? Nice story. Actually, in 2009, we got the correct answers on all the data sets. So in the competition, and that's the result, and we got the best benchmark award. And that result changed a lot of people's mind because previously people believed that it's not possible to discover causal direction without time information, right? It's the ID data. However, you can. So a lot of evidence suggests that you can easily find a causal asymmetry. As a consequence, you can really discover the whole direct secret graph or DAG graph from data. Okay, even if you have only two variables, yes, it's solvable. Now you are going to see how. Okay, so here you can see the scalar plot. Basically, we just make use of the distributional information. to discover which one is the cause and which one is the effect. For example, you have two genes, right? You can try to, just from the values, you can try to figure out which one is the cause. How? Remember, when we say this causal process, from rain to wet ground, there are some other factors, omitted factors, right? We don't measure them, and they are independent. The noise term would be independent from the cause. Okay? This is called independent noise condition. Good? And then this causal process can be represented by the so-called functional causal model or structural equation model. Essentially, it just represents the effect as a function of the cause together with omitted factors of noise, as you can see from here. Right? This is the general form. However, if you use the general form without any condition on the function, then you cannot distinguish between cause and effect. You don't know whether X or Y is the cause. But if you make some assumptions on the mechanism, then X and Y will become asymmetric. They are not symmetric anymore. Causal inference is not symmetric, right? X is called Y is effect. I know, yes, it is a one-directional influence. And if the data, the generation process follows one of those assumptions, then generally speaking, we can figure out which one is the cause and which one is the effect. The first one is called the linear non-Gaussian acyclic causal model. It's very simple. Effect is a linear function of cause plus noise. Okay? The second one, additive noise model. And last one, post-nonlinear model. With this model in 2008, basically we got the right answer on our data. So here we have two nonlinear functions. Why? Because this function F2 is very useful to measure, to model the measurement distortion, the nonlinear distortion. Because in biology and a lot of fields, we always have sensor distortion or measurement distortion, right? If you use some instrument, then you can just you just convert all values to positive one, then they are distortion. So basically, with all those models, you can see in the right direction, the model holds true, but in the wrong direction, you cannot find independent noise anymore. You'll see how. In the linear case. Now, as long as this picture is clear to you, it's good enough. So I first generate X, and then I generate Y from X. In other words, X causes Y, right? Because I generate Y from X together with the independent noise D. Okay, this is the generation process. Now, let's first consider the Gaussian case. In this row, everything is Gaussian. X is Gaussian, E is Gaussian. As a consequence, they are jointly Gaussian, and all X, Y, everything will be Gaussian. Here you can see, yes, I can try to explain Y with X by doing linear regression. And whenever I do linear regression, by construction, the residual will be uncorrelated from the predictor. And hence, they are independent because in the Gaussian case, if they are uncorrelated, they are independent. But remember that yesterday we were talking about that. So in the Gaussian case, if they are uncorrelated, they are independent. Now you can see, yes, in both directions, when I try to explain Y with X by doing linear regression, or when I try to explain X with Y by doing linear regression, I find an uncorrelated regression residual, and they are independent because Gaussian. However, in non-Gaussian cases, that's not true anymore. Here, X, the cause, and the noise follow the uniform distribution. This is as an illustration. So if I try to regress Y on X, now you can see I just try to recover the two processes, right? Then recover the residual or the noise would be independent from X because this is the true process, right? However, if I try to regress X on Y, as you can see from here, I do linear regression. By the way, the same thing holds true even if you do nonlinear regression. But now if you do linear regression, you see, yes, the residual will be uncorrelated from Y, but clearly they are not independent. So now you can see in the non-Gaussian case, if they assume the causal direction is not correct, then the residual cannot be independent from the hypothetical cause. Good. Now we can figure out which one is the really true causal direction. Here, we just rely on non-Gaussian distribution because in the Gaussian case, just because of the equivalence between zero correlation and independence, we cannot do so. But in any non-Gaussian case, we can. Okay. Now it's a linear case. It's very simple. If the causal direction is not correct, then I cannot find independent residual. Interestingly, the same thing holds true even if you use a nonlinear model, nonlinear regression model. So here, I generate y from x. Y is a nonlinear function plus noise. And to make it very simple, I just use a piecewise linear function. This is nonlinear function, right? Y equals nonlinear function of x plus noise. So if you look at y from x perspective, now you can see the noise will be independent from x. However, if you try to regress x and y in this way, now you can see clearly the distribution of the residual will be sensitive to the value of y. The same thing holds true. So in the wrong direction, you cannot find independent residual. Again, you find asymmetry between cause and effect. And it's quite intuitive. Why? Because the causal process is kind of natural, right? So if you follow the causal process, you can easily find independent residual. The word is very simple. You can first say something about the cause, and then say something about the conditional distribution specified by the model, function, and noise. The two modules are not related. It's very simple. But in the wrong direction, if you first say something about the cause, effect, and then say something about the cause, now you can see, yes, how you actually describe the cause x given y would be dependent on which value you are talking about, which value of the effect y you are talking about. So now the word is so complicated, you don't have modularity property. Right? We know that the most fundamental property of a causal system is modularity. Although the world is so complex, if I have a causal view, I decompose the whole system into a lot of irrelevant independent modules. Those modules are not related, right? So it's very simple. We can always do divide and conquer. We can change something here. We know this change will not affect any other module, right? Of course, the values will propagate, but it will not change any other module. This is the basic property of a causal system. And this is why we can build very complex aircraft. We decompose the job into a lot of modules. And you can take up this one, I take up that one. As long as each module is good, we can put them together, right? Modularity is so important. Okay, now you can see, yes, if you follow causal direction, you can find a very simple representation with independent noise. Otherwise, you cannot. Okay. Now, in the linear case, there are very efficient methods to estimate a model. And the model is known as a linear non-Gaussian acyclic model, linear non-Gaussian acyclic causal model. Each variable or node is a linear combination of the direct causes plus independent noise. Or this is a matrix form, right? I just put x together as a vector, then I have matrix form. And here, for simplicity, we assume there are no self-loop because we cannot identify self-loop. By self-loop, I mean the inference from xi to itself. Right? We assume there are no such a thing. As a consequence, all diagonal entries of B will be 0. Okay? And then we try to estimate this matrix form or those equations from data. And this is basically causal discovery in light of the linear non-Gaussian model. Here you can see the equivalence between the causal graph representation and the equations, the set of structure equation models. So here, x2 is determined by exogenous noise. x3 is determined by x2 and noise. Therefore, there's a causal inference from x2 to x3, from this guy to this guy, right? This is structure equation model. The variable on the left-hand side is determined by the value of the variables on the right-hand side. So they are not symmetric because this is structure equation model. Sometimes we just use a different notation. We can put right here, semicolon here, to mean that this is the assigning process, value assigning process. And similarly, x1 is determined by x2 and x3. As you can see from here, x1 is determined by x2 and x3 with coefficients minus 0.3, minus 0.2 and 0.3. So they are equivalent. Okay. So as long as you can recover this set of equations here, or the metric form, you have the causal model. Okay. Now the problem is how we can estimate the models from data, just from observational data. So a closely related problem is known as ICA, independent component analysis. It's a classical method, linear method for blind source separation. So suppose all of us are talking at the same time right here, and suppose we have so many microphones, right? Now, can you try to recover each of the individual speech signals from the mixtures, right? Suppose we don't know the mixing function because people can just walk around. In this case, this problem is the blind source separation, and ICA is a classical method to solve this problem. And here is the setting. Later you can see why I'm talking about the ICA right here. So we have a mixing function here. Basically, we just mix the individual speech signals to obtain the recorded signal right here. But we don't know it. We just know, yes, here I have some individual signals. I have mixing procedure, but it's unknown. Now I have a mixture. So in ICA, you try to apply a linear transformation. You tune the parameters. You make the output independent. And finally, if they are independent, you recover the original independent sources. Okay. Now this is cool because in principle, I only analyze, say, the two observed variables, x, y, x2, record the signals. I don't know A, I don't know S. S is the data matrix of the independent sources. A is the mixed matrix. I don't know that. Now clearly the system is underdetermined. But by making use of independence between the S resources, we can recover the mixing procedure A without difficulty. Why? Because we assume at most one of the SI's sources is Gaussian. That's why non-Gaussianity is so important. Later, you see actually in the world, signals should be non-Gaussian instead of being Gaussian. Okay, so if at most one of the sources is Gaussian, then we can recover A. That's it. This is ICA. And here you can see the intuition. Why? In the Gaussian case, right here you can see the scatter plot of Gaussian signals, right? And no matter how you apply the linear transformation, in this case, no matter how you apply a rotation transformation as a specific type of linear transformation, they are still independent, right? So meaning that if you want to make the linearly transform the signal independent, it's not strong enough to really determine where or how the transformation should be applied. However, in non-Gaussian cases, as you can see from here, this is a mixture of two super Gaussian signals. Is right here the mixture of two uniform sub-Gaussian signals. Here is the underlying signals are super Gaussian and uniform and super Gaussian, right? Doesn't matter. In all those cases, you can see you have to apply the linear transformation this way, or you can just keep going, right? You can just rotate it by another, say, 90 degrees. Then basically, you can switch, or you can change the order, you can change the sign and everything, but it does not really affect the independence. All you have to do this way and this way. In non-Gaussian cases, you can really recover the underlying individual independent sources, right? As you can see from here. In the Gaussian case, that's not true. Okay, as long as this is clear enough, that's good. Because if the problem is well defined and you know you can solve the problem, you can just use the maximum likelihood estimation or mutual information minimization to solve the problem. This is ICA. So here you can see illustration. We have the signals. We have no idea what the underlying sources are. Here you can see scatter plot. And then we can apply ICA. After first, second, or third iteration, you can see finally, yes, they become independent, as you can see from the scatter plot. And actually now we can see that the underlying signals are sinusoid waveform and some kind of super Gaussian noise. We can recover those things automatically by making use of only independence criteria for the outputs. This is ICA. Okay. Now, suppose we are familiar with ICA, which is already a kind of very fancy method. If you want to recover the underlying truth, very often time the linear ICA or some constrained version of nonlinear ICA could be very useful. Now let's try to recover the linear non-Gaussian acyclic model. We want to estimate the causal model from data. Now you can see a close connection between linear non-Gaussian causal model and ICA model. Remember, this is the linear non-Gaussian model right here, matrix form. Or I can put E on the left-hand side. E would be I, identity matrix, minus B times X. Right? It's just a linear transformation. Okay? And this is ICA model. I want to apply a linear transformation to X, X1, 2, 3, so that the component Y are independent. Now you can see here, we want to achieve independence among the component Y. Here we assume the knowledge term are independent. They are the same thing. Right? So W will correspond to I minus B. Now you can see, first I can apply ICA to the measured variable, the Xi. And then I can try to go from W to B. If I have the B matrix, I know everything because B is the weighted causal adjacency matrix. Okay? So how? We cannot really talk about details, but basically only two steps are needed. First of all, we know By ICA, I can find W. Second, let's see how we can see phi from W. First, we permute the rows of W to make all diagonal entries non-zero. Okay, and then we just divide each row by diagonal entry, and then we just take the difference of I identity matrix minus that matrix would just give the causal adjacency matrix. We have a standard procedure. Okay, so you can show that the solution will be unique. You can discover the causal relation among the xi measured variables uniquely in this way. Hey, now let's just look at example. Suppose this is a W matrix, the mixed matrix in ICA. Hey, now we want to find the causal adjacency matrix B. What can we do? First, we do permutation, as you can see from here, so that the diagonal entries are non-zero, and then we divide each row by the corresponding diagonal entry, as you can see from here, and then this is the causal adjacency matrix, I minus this guy. So we find the causal relation, as you can see from here. Okay, so now there are no difficulty. Even if you have, say, 2,000 variables, you can apply the same procedure. You can find a causal relation among the 2,000 variables in the linear non-Gaussian case. Okay, and furthermore, we know that in the nonlinear additive knowledge model case, the same thing holds true. Although in the nonlinear case, generally speaking, the computational load would be higher, because in the linear case, it's very simple. I can do permutation with some kind of heuristic method. I can make it very efficient. But in the nonlinear case, generally speaking, much harder. But in theory, there's no problem. You can just discover the whole DAG, directly a secret graph from data. Okay, so basically, I hope the message is very clear. And now you can see we don't need a basement assumption. Don't have time to talk about why, but basically now you can see a crucial assumption underlying causal discovery is dropped. Of course, we have to pay the price. The price is that we have to assume something about the causal mechanism. Is the linear non-Gaussian model or nonlinear model with additive knowledge opposed to the linear model and so on. But as long as this causal generating process is constrained, we have identifiability, we can recover the truth uniquely. Here, later I can just share all the data. This is the Gaussian's body height data collected more than 150 years ago. So you can see, if you apply this method, you can immediately find the causal graph. You see, gender and father's body height and mother's body height together cause the body height of the child. Okay? So everything is transparent. You can really discover causality just from this kind of IID data. Okay? So now you see the idea. I will just skip the method for additive math model. Here you can see some application. We analyze the stock market in Hong Kong this way. You can see there are many interesting things. Of course, we know that in the market there could be a lot of hidden variables. If you just assume there are no significant hidden variable, you can see here there's a significant influence from X8 to X5. X8 is a Hang Seng Bank. X8 is HSBC. And we know that HSBC holds something like 60% of Hang Seng. So if company A owns company B, then they are the causal influence from B to A. Why? Because essentially B is a part of A, right? So you can see a lot of asymmetric relations right here among the big companies by doing causal analysis. Okay. And here we assume in the linear non-Gaussian case, we assume the variables are non-Gaussian. Do you think that's a plausible assumption? Do you think variables are non-Gaussian? First of all, we know yes. Very often we assume Gaussian distributions for multiple reasons, right? Because of the central limit theorem and also because of simplicity and so on. But in reality, generally speaking, variables should be non-Gaussian. This is the Kramer decomposition theorem, which I was mentioned yesterday. So we have the linear closure property of a Gaussian distribution. If the sum of any finite number of independent variables is Gaussian, then each of them is Gaussian. Meaning that if I receive any non-Gaussian contribution from any non-Gaussian guy, I'm non-Gaussian. So in the world, as long as you see some non-Gaussian variables, and as long as you believe this non-Gaussian thing contributes to other things, then all those things will be non-Gaussian instead of being Gaussian. Okay? So that's why in reality, Gaussian. Of course, in reality, they may be close to Gaussian. Why? Because central limit theorem says asymptotically, if you have the sum of infinite number of independent variables, under some conditions, it's going to be Gaussian, right? So it's an asymptotic case. But we are talking about real case with a finite number of independent variables is actually non-Gaussian. So we are happy because we know it should be non-Gaussian. Good. To summarize, I just talked about the classical method for causal discovery. We started with a traditional method making use of conditional inference relations. And the first message is that learning causality is not mysterious. Of course, we need assumption. Remember the question for a 4-year-old in kindergarten, right? So yes, we can answer the question. The issue is we have to make assumptions, and fortunately, in many cases, the assumptions are testable. Linear non-Gaussian model assumption is testable, right? You can see whether relation are linear, and you can see whether distribution is non-Gaussian. So basically, with those methods, you can discover causality. Now let's go one step further. Let's try to allow a lot of latent variables in the system and try to see how we can discover everything from data. Okay, you are familiar with this picture. So basically, with causal discovery or causal representation learning, we try to find underlying causal structure together with hidden variables with identifiability guarantees. We rely on modularity property, and the modularity property can instantiate or can give rise to some statistical constraints. We make use of them. Now let's consider a broader setting. Basically, there are 3 axes of the setting. First one is whether you have ID data. Okay, in causal discovery or causal representation learning, if you have non-ID data, by ID I mean independent and identically distributed data, right? If you have non-ID data, the problem will become easier. Why? Because causality basically is a way to understand changes and also a way to apply changes. If you see changes or temporal information, you can leverage them to discover causality in a better way, right? So in the ID case, you only have a single distribution, but if you have change distributions, basically someone like nature already applied the intervention, right? You have multiple distributions and it can easily discover causality. That's why we have to distinguish between ID case and non-ID case. And if you have parametric constraints like linearity assumption, then you can benefit from it. And generally speaking, we allow a lot of latent variables. Now you can see a summary. This is a summary of the recent results in this particular field. So you have ID data right here. You have non-ID, but ID data. This means you have time information. The first I stands for independent. The second one stands for independently distributed. So here you have non-independent data. So you have temporal dependence. And in the second case, you have independent but non-identically distributed data. You have multiple distributions, right? You may have non-stationary data or you have heterogeneous data collected under different conditions, for instance. So now you can see in the ID case, generally speaking, we have equivalent class, generally speaking. But if you make parametric assumptions like a linear non-Gaussian model, then you may have a unique identifiability. Okay? And in those cases, if ID assumption is validated, generally speaking, we have better identifiability. I will just give you examples to illustrate all the results. And if you want to see more details, you can just refer to the papers. All the papers are mentioned in the presentation. Okay, so here in the ID case, basically, you already saw all the story. This is the first example. In archaeology, they try to see causal relations. We have ID data. We don't have parametric constraints. We may or we may not have latent variables. We can use conditional independence to recover causality, right? So here you can apply PC or FCI. As you can see from here, this is the procedure you saw yesterday. And then we can see the result, which you already saw yesterday. Okay? So this is already part of causal representation because we consider causal representation as a broader task of causal discovery. You just allow a lot of latent variables. Okay, so this first example. Now you just saw this. If you make some parametric assumptions right here, you have ID data, you can benefit from parametric constraints like this one or that one. Then you have better identifiability, right? And this is a particular example. So here, we analyze the data. We have 2 variables, x1 and x2. We just have the values or scatter plot. And then if you assume x1 causes x2, you can fit the model, you can estimate the residual, and you can see they are independent. But if you assume x2 causes x1, as you can see from here, then you can see the residual cannot be independent from x2. As you can see from the scatter plot, of course, you can do independent test. So here, actually, x1 is the altitude of 300 cities, and x2 is a corresponding precipitation. Clearly, altitude causes precipitation, not the other way around, right? You can really recover this asymmetric causal influence just from the scatter plot of the values. Okay. And now let's go one step further. This is more interesting and more practical. Each of us try to understand our personality. We want to see how we are similar and we are different, right? How can we discover personality? What's personality? Personality might be the underlying kind of, say, the behavior of aggregated neurons, right? But we don't know. In this case, we can only design questionnaires. As you can see from here, we have different questions, and then different subjects can give answers. We just have answer scores to the questionnaires, right? They are always observational data, and they are not really true causal variables like pixels. They are not really true causal variables. They are just reflections of the underlying true variables and relations, right? So in this case, how can we analyze the measure the variables to recover the true process? So let's define the problem this way. We have xi's, we measure xi's right here. And xi's were generated by a lot of hidden variables. And hidden variables can also be related, as you can see from here. Okay? And this is the general model, basically with the hidden variables. And you can make it more flexible. We can even allow influence from measured variable to hidden variables, anything defined. However, you are going to see that this model with a lot of hidden variables can also be estimated from data. Okay? So I'm going to talk about two methods. The first one basically relies on the rank deficiency information of the covariance matrix. In the linear Gaussian case, we can only make use of covariance information. But the rank information of the blocks of the covariance matrix can give you causal information in the linear Gaussian case. You'll see why. And the second one, in the linear non-Gaussian case, we can go further. We can even determine the causal direction and the structure over all the hidden variables uniquely, okay, in the linear non-Gaussian case. So basically, you can just discover the hidden variables and their relations as if they were directly observable. This sounds kind of amazing, right? It's mysterious, but later you can see why. So here, first of all, suppose this is a causal graph. All the hidden variables are just Li. So Li variables are hidden. And we have Xi variables as measured variables or observed variables. Now, can you measure or can you recover the hidden variables? For instance, let's focus on L6 right here, L6. Can you determine the existence of L6 from data, from the data of X? Can you? Now, now we only have X variables. Can you? Let me ask one question, okay? Now, let me ask one question. If you look at X10, 11 right here, 10, 11, now you can see X10 and X11 are related to all the remaining variables only via a single variable, L6. Is that right? That's very strange. This means mathematically, the cross-covariance matrix, that's the covariance, the rectangular matrix consisting of the covariances between X10, 11 and all the remaining variables will have rank 1. This is rank deficient, right? In the general case, if there are two ways for them to be related, the rank will be 2. Okay? If they are independent, the rank will be 0. Now you can see the rank will be 1. What does it mean? It means that there's only one bottleneck to relate X10, 11 and all the remaining variables, right? Now can you determine the existence of L6? There's only one way for them to be related. And I can further make sure that this one, the bottleneck is not measured, is not Xi variable. Then this guy must be a hidden variable. I can determine the existence of L6. Is that right? So basically, this is a very fundamental observation you can make use of. So you can determine the existence of L6. That's it. Similarly, after you do that, you can determine the existence of L2. Why? Because you can see X4 and L6, or its surrogate X10, 11, are related to all the remaining variables via a single guide. You can determine that. So this way you can determine the existence of all the hidden variables. And furthermore, you can recover the whole graph, including hidden variables up to the Markov equivalent class, because this is linear Gaussian case. In the linear Gaussian case, we can never go beyond the Markov equivalent class because we just have a conditional independence or covariance information. And furthermore, interestingly, you can see previously, remember, we made use of conditional independent relations to discover causality. That's a special case. Why? Now, suppose this is the case. Suppose the rank between X1 and 2. The rank of the cross-covariance matrix between 1 and 2, and 2 and 3 is 1. What does it mean? It means there's only one way, only one guy, one bottleneck to relate X1, 2 and X2, 3. X2 is shared. This means X2 is the only way for X1 and X3 to be related, meaning that X1 and X3 are conditionally independent given X2, right? So now you can see the rank division information is kind of very informative. It also contains conditional independent relations as a special case. That's why now by making use of rank deficiency constraints on the covariance matrix of all the measured variables, we can determine latent variables and relations. Okay. Of course, the method is very tricky because you have to make use of the constraints in a recursive way, but the idea is clear. Now, let's look at the result. Remember the personality data. We have so many questions. Actually, they designed the question this way. They made use of their understanding of big 5 personality traits. By big 5, I mean ocean, OCEN, openness, conscientiousness, extroversion, agreeableness, and neuroticism. They believe that those 5 dimensions can capture the personality, right? And then for each of them, they designed some questions, as you can see from here. Here we have O3, can you see? O3, O6, and so on. So we have answered. We consider each of them as a measured variable. Now we apply the method. Then we could automatically discover all those hidden variables, okay, together with the relations. And if you have a closer look, you can see, first of all, in some way it's consistent with the big 5 personality traits, but it's clearly more informative. And you can even immediately find ways to do intervention to make your personality better in the way you want. I'll give examples. For instance, if you look at this one, this is the hidden variable underlying agreeableness. And this is the hidden variable underlying extroversion. You can see the causal influence from this guy regarding agreeableness to extroversion. What does it mean? It means that if I want to be more extroverted, then a natural way to change my cause, I can try to say, learn to be more agreeable to others, and then I will become more extroverted. Because you can see the causal influence, right? And you can even have a closer look at the openness questions. Right here, we have so many openness questions. We discovered 3 hidden variables instead of 1. If you look at the questions adjacent to the hidden variable, you can see here we have 3, L1, L6, and L4, right? L1 is about imagination, and L6 is about understanding things, okay? The ability to understand things. L4 is about kind of coming up with ideas or creativity. And furthermore, we know that understanding and imagination are both causes of creativity. That's true, right? And now you can see because of the technologies, a lot of people are becoming better and better at understanding things. Because if I don't know it, I can quickly use Wikipedia to see what's going on. However, at the same time, imagination can be worse. As a consequence, creativity can be worse, right? So actually, this happened to a lot of students in my group. So in that case, we have to find a way to encourage the student to be more imaginary, right? They have to practice their imagination skills. How? For instance, we can just we make sure they don't use, say, electronic devices or internet, right, to find answers. They have to sit there independently to come up with some solutions, right? This is the way to practice their imagination. And of course, imagination, as you can see from here, is the essential component of creativity. So from this result, you can really figure out a lot of possible ways to do interventions to improve particular dimensions of personality. And here we analyze the 50 questions. We also had results on 120 questions and the one with 300 questions. I don't dare to look at the result because whenever I have a closer look at the result, I feel like I want to change something about myself. You can see how, right? To change a particular dimension, you can really figure out the causes and you try to see which one can be easily changed, and then you can try to achieve a difference. Okay, so now you can see in psychometric studies, we can easily discover the underlying hidden variables, and we can understand the causal relations. It's perfect. Now let's go further. Now let's make use of linear non-Gaussian model. Suppose the noise from the non-Gaussian. That's the only assumption, in addition to linearity assumption. The question is right here, can you discover the causal direction between L1 and L2? We know that in the linear Gaussian case, we cannot. In the linear non-Gaussian case, the message is as follows. Yes, it's just like previously, remember, in the linear Gaussian, non-Gaussian case, we can figure out which one is the cause and which one is the effect, right? Because in the wrong direction, you cannot find an independent residual, remember? Now the same thing happens. So even if they are hidden variables, we can do the same thing. I'll skip the details, but basically, we can just see if this guy is the cause, if L1 causes X2, then we can find a linear combination of X2 and 3, which is independent from X1. But if the direction goes this way, we can never find a combination of X1 and X3 that is independent from X1. Hey, that's it. So this is because of a very famous theorem called the Darmois-Skytovich theorem. So that theorem is one of the beautiful theorems in mathematical statistics. Basically says that if we, as two variables, receive the contribution from the same non-Gaussian variable, then we can never be independent. Okay, that's it. So we can find the asymmetry. Now we can determine the direction between hidden variables. And more broadly, right here, we have the gene condition, generalized independent noise condition. Essentially the same thing. We try to see whether there exists a non-zero linear combination of some measured variables that is independent from some other variable. That's it. And if that's the case, we can see some graphical condition. I will skip the details. If you want to have a look at details, you can just refer to the papers. And the beauty is as follows. By checking the gene condition, which is very simple, right? Which is involved independence between combination of measured variables and some other measured variables, you can first of all figure out which measured variables share hidden variables, and second of all, you can figure out the causal order of the hidden variables. Everything is given. As you can see from this result, I'll skip that. This is known as the teacher's burnout data. So they try to see why teachers are tired. They measure 28 variables. With this method, we recovered a lot of hidden variables, and we recover the causal order of the hidden variables. On the right-hand side, right here, on the right, you can see this is the hypothesized model given by experts. They are basically the same thing. Meaning that, yes, the experts are very good. They produce a model that can really explain the data. At the same time, computational method is very useful. You can really recover the hidden world involving hidden variables and relations by making use of the measured indicators. Okay. Good. Now, let me just, okay, we have a couple minutes. Good. For this part, now let's go from the ID case to the temporal case. With the time information, it's much easier. A classical way to do causal analysis is to make use of Granger causality, right? Granger says Granger causality not necessarily true causality, but under some assumption, Granger causality true causality. So here, you see, we started with Granger causality because here we try to see the relations among the measured variables, and then we try to recover hidden variables. For instance, you can try to discover the information of objects and relations from video data, right? And then we can have some extensions to make it more practical. Right here, this is the Granger causality. There are two principles. Future cannot cause the past, and there are no redundant information, meaning that here, if xt the cause of yt plus 1, then XT contains uniquely useful information for the prediction of YT plus 1. That's it. And then this is a Granger's 1980 paper. It's different from the classical paper. In this case, you can see Granger defines X causing Y this way. This looks complex, but basically it says XT and YT plus 1 are conditionally dependent, giving all the information up to time t without XT. Now you can see, you can understand Granger causality as a conditional independent based way to characterize causality in time series. That's it. It's also conditional independence. And of course, right, you have to assume the resolution of time series is correct and that there are no latent variable. Then Granger causality is true causality. However, we try to consider the causal relation just among the measured variables. In practice, very often time that's not true. For instance, right here, we have video data. You can consider video data as a high-dimensional time series, right? You consider each pixel as a variable, then video data is nothing but a high-dimensional frame by frame, right? It's just high-dimensional time series data. Now you want to understand, you want to do video understanding. You try to see what's going on behind the video. What can we do? So here, it's amazing. You can allow everything to be non-parametric. So right here, we have X as a video, high-dimensional time series. We assume that the video data is nothing but a function, flexible, nonlinear function, invertible function of the underlying processes, latent process like kind of balls and the relations. And then for the ZT processes, Z1T, Z2T, Z3T, and so on, they can be causally related. However, if you have high resolution, then when you use the true causal processes, there are no instantaneous relationship. Why? Because if you use a true causal variables, it takes time for causal influence to take place, right? There are no instantaneous dependence. Given the past, we are conditionally independent because there are no instantaneous relationship. If you influence me, it takes place up some time, right? That's the only assumption. Basically, with that assumption, even if the function is non-parametric and the relation between the hidden variables are non-parametric, doesn't matter. Generally speaking, you can recover all the hidden variables without any difficulty. Okay? Here you can see a very simple illustration. You can see the data. This is the mass spring data set. We have 5 balls with different colors, and between some balls, there are hidden springs. They are related. With this video data set as input, immediately we can recover 10 processes. And they just correspond to the X and Y coordinates of the 5 balls. So you recover the 5. You know, basically, I can forget about video data. I just pay attention to the 10 variables. They just specify the 5 balls. At the same time, you can also recover the causal relation between the balls because of the hidden spring, right? You can recover everything from video data with a clear interpretation. So basically, this is how we can make use of temporal constraints. And here you can see we can even allow the function G to be non-invertible. Doesn't matter in practice because G maps a 3-dimensional world to the 2-dimensional video data, right? May not be invertible, but doesn't matter. Under some assumptions, you can solve the problem. This was, I think, ICML 2023. And furthermore, you can even allow instantaneous relationship among the latent variables. Some relation may be very quick, right? They're instantaneous. Doesn't matter. You can still do something. Okay. So I think maybe I should, because the last part is closely related to the next one. Yes, maybe we should take a break right here.
Thanks, Professor, for the information. If you have any question, we will not have much time for the questions.
Which one?
If your graphs has bidirectional errors,
yes,
cause to the event and so how will you handle that?
Wonderful. Actually, I intended to include something here, but it's too time consuming. Bidirect link can mean different things. In one case, it can mean latent component. Remember? Let me go back. So right here, remember in this case, if you want to explain the relationship between X2 and X4, you have a bidirect link, meaning that there are latent variables in between. This is one interpretation. The second interpretation is to say, right here, I have a cycle. X2 could influence X4 and X4 could influence X2. If there are cycles, you can still discover cycles. And actually, it's interesting to understand the cycles. If you have the, I think yesterday, someone explained this problem. So if you really have the time series data, then there are no cycle. XT influences YT plus 1, YT plus 1 influences XT plus 2, right? So there's no cycle. But the problem is, very often you may have low resolution data. You can have the aggregated data like stock returns, daily returns, the aggregation of the short-term returns, right? Or you can have equilibrium set data, right? And then in that case, in the data, you can discover cycles directly. Okay, but we know if you want to understand why you have cycles, you go to the true time series or stochastic process, there are no cycle. And this is the second interpretation. And give me 1 second. Is there any other interpretation of bidirect links? Or in some cases, yes, the third one is to say that I don't know the direction. Both directions are possible. And in our framework, usually we just use the undirect link to represent it, as you can see from here. Sure. Yeah, if you don't know the direction, we just use undirected one. But some people use the bidirected one. In that case, if you are willing to make some assumptions, then generally speaking, you can find a causal asymmetry. Did that answer your question?
Yeah. Professor, you can discuss with the professor speak later on. We have another question from the student.
I have a very basic question. Before the work you have shown for the Lingam paper of 2009, the distribution error E1 was non-Gaussian. And then later on, you put the model to a non-linear model without any approximation. This might be working for us for a small number of temporal density, but as the density increases, there should be some model which should be in between so that non-linearity and linearity should be addressed. Like if you see your slides, like in the very basic slides.
Give me a second. I guess you are referring to something like this one?
Yeah. Before this, like when you were talking about, yes.
Yes.
Before this, when you were talking about, when we were assuming about the model distribution, the Gaussian model, it was a Gaussian model, and then later on, you put the model to a non-Gaussian model. Like there's a non-Gaussian data. There's no approximation which is present in between that.
So you are saying there are no kind of intermediate thing between two?
Yes, exactly. There's no intermediate layer which is in between those two.
You mean between, say, this one? Is that what you mean?
Yes. Last one.
Last one. This one?
Yes.
You get no intermediate one between this one and this one. Is that what
yes,
you mean?
exactly. Like from a linear model, you're going directly to a non-linear model. And also there's no layer which is in between them. There's no approximation layer, and you're only abbreviating it with the error E. Like where's that approximation model?
So can you give an example regarding the approximation model or something in between?
For example, like we have a data set of patients of same class, and there are certain outliers which are in between them, and we do not have a normal distribution there, and we have some Poisson distribution which is added to it. Then for that case, there should be some distribution mapping which should be present there, because the way I see it in the future work where you have shown the work of the grad, that would not be so much validated.
Maybe you can.
I think it's a debate or discussion, so we keep it for later time.
Summarize.
We have only one question left.
Good question. I'm trying to see exactly what you.
Yeah. So my question is about the.
Oh, okay. Let's talk about it afterwards. In that case. Okay. Thank you. Go ahead.
Yeah. So my question is about the personality traits slide. So you showed how different personality traits are related based on that causal relationship. But I have a more basic question. You showed that the questionnaire, they answered the questionnaire, and you had different responses for different people.
Yeah.
is there a way to find out that did the respondent actually replied correctly for each question, or maybe they were hiding maybe they were faking some information? Is there a way to find that out?
Wonderful. Okay. Wonderful. Yes. When you say basically, you say the answers could be biased, right? I can pretend to be another type of person, right? So when you do that, there are only two possibilities. One is to try to fake or try to hide my original genuine answer to a particular question. If that's the case, then this is noise. Is that right? Because this is basically only applied to a particular variable. And if you just try to apply the same thing to multiple answers, then you are going to introduce another hidden variable. You can also recover that from data. If you analyze the data set with 120 questions, you can see a lot of hidden variables. Indeed, people try to hide them, kind of try to, in some way, try to hide their genuine kind of attitude in some way. So that thing can also be discovered from data if you have enough questions. Because if you have only one question, it's noise. If you have two, it's a latent variable. You can recover it. Is that answer to your question? That's a good one. And so basically, from my perspective, data does not lie, and you can really recover the whole generating process. Even the mental condition underlying the mental condition you have when you answer the question, right, could be recovered from data because it's a code. What? Oh, counterfactual. Yeah. Yes. Actually, after that, you can do counterfactual. You can try to whenever you do counterfactual, you have to use the causal model, right? You can after that.
Thanks, Professor. You can discuss with the students later on. Now we move to the next session, causal generative AI.
Okay, fine. Sorry. Oh, no, we will finish everything within 15 minutes. That's good. Good. Sorry. Oh, let's go. Okay. I think 15 minutes.
Oh, 15?
Yeah, 50.
50.
Okay. Yes. Okay. Now, welcome back. So let's see more exciting things right now. Now we have multiple distributions, right? Because we are talking about a violation IID assumption. So in this case, you have multiple distributions. From a causal perspective, it's so nice because it captures changes. With causality, you want to explain changes or apply changes. That's why it's beautiful. Remember this story I summarized right here. From the two clinics with almost the same techniques but very different mortality rates, he discovered the hidden cause, and based on the understanding of the hidden cause, he proposed the intervention. The world became different. So now you can see, we make use of two different data sets. We can discover the hidden cause. We can make a difference, right? That's the message. In machine learning, it's the same thing. We just have a principled way to do so. Look at this example. We have two data sets. This is the original MNIST data set, and right here you have another one. What's the difference? What's the changing factor? What's the underlying cause of the difference from your perspective? You don't know the parent information. You don't know this guy corresponds to that guy, right? But you have a look. Suppose they are produced by aliens, okay? But you just look at the shape. Can you figure out the difference between the two data sets or domains? Yes. Then rotation, basically. Yeah? Rotation, perfect. However, mathematically speaking, in this case, we are trying to go from the marginal distributions to the joint one because we try to see how they are related and how they are different. In mathematics, this problem is clearly ill-posed because how can you go from the marginal one to the connections, right? But for us, we can easily solve the problem. Why? Because we already made use of some principle, simplicity principle. Similarly, let's consider another one. we have a set of summer images and another set of winter images. Suppose you see enough. It's very hard for you to see paired data because it's almost impossible to stay in the same place for half a year, right? So suppose that's the case. Now, if you are given a summer image, can you produce a counterpart in the winter? Meaning that you have to understand season. You have to understand the difference across the two seasons, right? Can we do so? We can, right? We can try to identify the difference and we can apply the difference. This problem is known as image-to-image translation, or if you want to generate two images with the same scene but different seasons, it's called multi-domain data generation. Basically the same thing. You try to see the correspondence information. You go from the separate marginal ones to the joint. That's the problem setting. It's ill-posed, but we can make the problem well-posed by making use of suitable simplicity assumption. What assumption? Basically, we know image has two parts. One is content, that is preserved, right, in the translation procedure, and the other is style. I try to explain the difference, right? When we try to understand what style means, we assume that the style should be minimal. As long as it's sufficient to explain the difference, it's good enough. That's why in the previous one, we said, yes, rotation is a difference, right? We just have a change in the angle. And here, we also know, yes, I can just add snow, I can just make some changes, I can change the tree, right? And so on. And then I can go from one image to a different domain, right? So mathematically, we can formulate this condition. It's called minimal changes. So the style variable or style component should have as few components as possible. That's it. Interestingly, if you make use of this assumption, minimal change assumption, with the minimum number of changing components as a style, you have identifiability. Meaning that you can go from the separate sets of images to the joint ones. You see the correspondence information and so on. And of course, this is a way for you to align different domains. As a consequence, you can do transfer learning. In transfer learning, you see you have some domains. Say in the summer, you collect images, you have labels, and then you are given, say, an image in the winter, and you try to make a prediction. The distribution is different, but now we can try to figure out how they are different, how they are related, and we can just try to introduce a minimal change to align them. Now everything is transparent. By the way, this is also how we can discover the law in the world. We discover laws how? We know F equals MA. How can you discover F equals MA? First, you see, yes, F, M, A are in different modalities, right? Force, acceleration, and mass. And you can see the dependence. You can see F is dependent on A and so on. But if you introduce M, mass, then you have a deterministic relationship, F equals MA, right? That's the law. Here, by introducing the minimal change thing, the world is becoming deterministic. X, the image, is just a function of the underlying content with this fixed mapping process, but there could be some style that can change, right? You can recover everything from data. As a consequence, you can do transfer learning. You can also do multi-domain generation or translation. Let me show one result. Here, we are given two separate image sets, data sets, corresponding to the female images and the male images. Okay? They are separate, and we don't have paired data, right? And then we are required to generate two images across the two data sets corresponding to the same content, the same person. With this principle, you can see, yes, basically we can generate two persons which are almost identical. If you forget about the gender, right? The gender must be different because we want to apply the difference. Now you can see, yes. But with other methods in computer vision, you can see there are actual distortions, eyeglasses and hair, right? So now you can see, yes, in machine learning, in modern machine learning, very often we have to deal with ill-posed problems. We can solve the problem because we make use of some kind of suitable kind of simplicity assumption. We have to formulate the conditions technically and make the conditions operational so that the machines can learn how to solve the problem, as you can see from here. Okay, now let's go further. More broadly, this is a kind of very mathematical, basically, we can discover the hidden world by making use of multiple distributions. We can even allow causal relations, chaining relations among hidden variables and everything. So this is a too broad, very general setting. If you want to research in this direction, maybe you can start with this paper. So this was published in last year at ICML. So basically, you can recover hidden variables with chaining causal relations from the measured variables right here. And this is a general setting because everything is non-parametric. You can still recover the underlying model in a non-trivial way. Okay. To summarize, in causal representation learning, we try to recover the whole causal structure together with hidden variables. This can be seen as a causal discovery with causally related hidden variables. And we can solve this problem. First of all, as I just mentioned, we have to formulate causal principles and make the conditions technically operational. For example, we have minimal changes, we have different kind of sparsity assumptions, and so on. And then we can solve the problem. And you have to establish identifiability because you aim to recover the truth. In the ID case, if you have independent and identical distributed data, then generally speaking, you can benefit from parametric constraints, right? Like a linear model. And in the non-ID case, generally speaking, you have stronger identifiability because you have more information. By more information, I mean you can have multiple distributions or you can have time or temporal constraints, right? Future cannot cause the past. Okay, so this is for this part. If you want to see details, please just refer to the papers or just email. Now, let's see how generative AI can benefit from causal understanding or causal principles. Okay, good. In this part, first, let's look at autoregressive text generation. Do you think this is really plausible? Do you think there are inherent problems? How can fix problems, right? And then let's try to focus on image generation. Let's see how we can understand the concepts behind the images and how we can manipulate the concepts to generate new images and how we can do image editing and so on. Okay. First, let's consider autoregressive model. Right now, autoregressive generation is a popular paradigm, right, for training and also of large models and also for text generation. It works this way. I have the first token, and then I predict second one, and then I predict second one, third one, fourth one, and so on. It's autoregressive, right? Ideally, do you think this is the way we follow when we try to produce text? Basically, we write down a sequence of text in order to achieve many things. We want to make ourselves clear. We have to make sure it's grammatically correct. We have to make sure it's smooth. And sometimes we pay attention to the transition. For instance, if you tell a joke, you have to pay attention to the transition to make it funny and so on. We want to satisfy so many criteria, right? In other words, we try to find the right token in all those, across all those places, right? To satisfy a lot of criteria. And this is similar to the hidden Markov model. So I observe something as a kind of reflection of the hidden world. And then I try to figure out the hidden variables, the sequence, right, to maximize like the function, for instance. And right here, we know that in order to estimate the base sequence for the hidden states, we cannot use the autoregressive way to solve the problem. We have to go forward and then go backward. This is how we can solve how we can find the hidden state in the hidden Markov model. They are similar. I just try to see which token I should use here, which token should be used here, and so on, right? To satisfy a lot of criteria. Is that right? And furthermore, we already discovered that in music signals, it's not really autoregressive generation. It's not really just autoregressive generation. It's not a temporal causal inference. Instead, there are many selection patterns. What does that mean? I have to put something here in this location. I have to put something there to make the music interesting and informative and smooth and so on, right? It's a selection. They have to satisfy some criteria so that they can become very nice music signal. It's not causal. Similarly, inside our bodies, a lot of genes are dependent. they are dependent not necessarily because they are causally related, right? Neither of them is the cause of the other. However, they have to work together in a specific way so that we are healthy humans. As a consequence, we are included in the data set. If they don't work that way, then they are not, basically, the subjects are not humans. They will not be in the data set. This is selection bias, right? There are no causal explanation, but you happen to analyze the data set collected from healthy humans. That's why they are dependent. Similarly, they have to be dependent in that way in order to produce a very nice music signal. Okay? But the first one does not cause the second one. Right? We verified that in music data, as you can see from this paper, music and the text are very similar. So in text, we also do something. Let me show one example to illustrate a big problem with autoregressive generation. Last year, I was translating a book, thinking things through to Chinese because I think the book is very good. Everyone should really enjoy thinking things through. So this is one sentence in the book. This is English, original version. Athens was an aggressive city-state that conquered and subdued, blah, blah, blah. You can see there are two words, conquered and subdued. If you want to do translation, what can we do? Here you can see the translation by GPT-4o. So sorry, sorry, this is Chinese, but basically you can see the problem. The two words are the same. The first word corresponds to conquer, the second one corresponds to subdue. Why do you think they are the same? Clearly, this is not ideal, right? And if you just see conquered, you can use this word. But if you see subdued, you know, oh, now I have to change this word because subdued is a kind of another level. They are similar, but they have a subtle difference, right? So I change this word. I can make it weaker. Then I can just make the translation smoother. But with GPT-4o, you cannot do so because it's autoregressive. You cannot do reflection to go back to make necessary changes. But as humans, we can. Once again, in some cases, we have to go back to the modifications, right? So just this year, we just published a paper basically based on this idea, the reflection window decoding for text generation with selective refinement. You can figure out when you have to go back to make modifications. And this is more like how we write long sentences or long articles, right? Sometimes yes, as time goes on, I may figure out, yeah, right, at the very beginning, I should have said something different. Then I can go back, right, to make modifications. Machine can also do the same thing. Okay? So why can we achieve that? This is because we care about the underlying causal principle and the causal process. Okay? If the causal process for text generation and our causal process are not consistent, the result cannot be consistent. So that's how and why. Now let's go further. By the way, I would like to share one paper with you. The language for basically the paper is very nice. Language is primarily a tool for communication rather than thought. In this paper, they said the language module can be separated from the module for thought or reasoning. So essentially, with language model, we try to build artificial brain. We have different modules. You have a reasoning module, you have everything, and language is basically just a particular module for communication. We shouldn't just try to incorporate everything in a single large language model. We may have different modules, and then we use language for communication. That's it. That's why representation learning and reasoning should be separate modules for large language models. Now let's look at the images. So for this project, I think 20 minutes will be sufficient, then we can get things done. Image generation is very nice because you can immediately see the result by making use of different methods or different principles. But in traditional causal discovery, very often it's very difficult to verify the result, right? Because you do causal discovery because you don't know the ground truth, right? With images, you can immediately see the benefit. Now, I'm going to talk about how we can generate images or edit images by making use of some causal principles. First, suppose we have labels. So suppose we are given a lot of labels like age, mustache, necklace, and so on. And we try to just have a controllable generation process. If you give me values of the set of features, I can generate the image for you. And if you change one feature, I can change the picture accordingly. right? Now you can see causality plays a very important role. This is a platform which we produce concept again. There are many features of the resolution very low. So right here, this age, this gender, and so on, you can just specify all of them, and then you can generate image. And you can change any feature or attribute. You can see a corresponding difference. Now, let's consider the following problem. Suppose you change age. Do you think eyeglass should change as well? Yes. And suppose you just want to change eyeglasses. Do you think age should change? Why? Because the causal asymmetry, right? So again, features are causally related. Change the cause can naturally lead to a difference in the consequence. But if you just change the consequence, you shouldn't change the cause, right? So, okay, wonderful. So everything clear. How can we, now the problem is how you can achieve that. Basically, we can make use of functional causal models. And if you just pretend the features are not relevant, it's a disaster. Why? Because the age information in the image and the eyeglass information can overlap, right? Because they are dependent. They can overlap. And if you don't model their causal asymmetry and just change, say, eyeglasses, when you change this part, you can see the reflection of age could also be different. Meaning that if you try to change eyeglass information, the age information can be different, right? However, we can use a causal way. The effect of eyeglasses could be a function of the cause, age, and some independent noise. And when you try to change eyeglasses, you don't change age. You achieve that change by making use of a difference in the noise term. This way, I can make sure age is the same. I only change the noise term in eyeglasses, right? That's it. So this way, you can capture causal asymmetry, and you can really apply the consequences of changing the causes, and also at the same time, when you change the effect, the cause will not be different for that reason. So we did that. Furthermore, we make use of minimal changes because we try to make sure the reflection of each of those features in the images are minimal. Otherwise, there could be extra distortions. Okay? We always make use of minimal changes. When you produce a painting and when you try to change something, you try to avoid extra distortion. So we also use that. Putting them together, we can just come up with a platform. So here, first, we find a causal relation among all those given features. And then, now you can see, if you specify anything in this platform, you can produce a picture. And if you make a difference, then you can see the difference in that feature and also the corresponding difference in the effect features. Okay, everything is natural. And here you can see some result. The first column is the result given by GPT-4o. The second one given by MBZUAI, and so on. The last one is given by our platform. So here you can have a prompt, girl with mustache. So you can see yes. Because of causality, you can really have a controllable generation. You can see mustache. But with this one, you cannot do it. With this one, you can see with GPT-4o, it's kind of a cartoon image because it's very, very unreal, right? And similarly, you can generate a lot of very interesting images with very nice controllability. Okay. So here we assume the feature is given. That's why you can just change the feature, you can see the difference. Next, let's go further. Suppose we don't have the explicitly given features. We only have text image pair, right? A classical way to make use of image text pairs is to use a CLIP model, right? CLIP model, comparative language image pre-training model. So this is the way to relate images with text by making use of something like a nonlinear CCA, nonlinear canonical correlation analysis. I try to see how they are related, right? I can find the features of the images and the feature of text so that they are heavily related. This way, I can draw the correspondence information between text and images. That's CLIP model. However, it's not causal. There are no identifiability. I cannot figure out the concepts underlying images and the concept underlying text. And I cannot see the precise correspondence information involving concepts. We use a generative model. And even before that, we made some modification. I think it's a CVPR paper. And now we are going to use the causal view to solve the problem. This is the problem with the current AI tools, generative AI tools. So you can generate very nice images, right? but they are not controllable. If you want to change a particular thing, other things can change. But we know that if you want to produce a very complex picture, you have to make sure it's controllable. Suppose you are a very smart artist. You produce something, you have a sketch, and they can make things more and more detailed. And if you think something is not very natural, you can just focus on one particular thing in a corner and make it better, right? So you always have concepts on your mind, and you just make necessary changes. How can we do so? As you can see from here, the generative AI tools, the popular ones, cannot achieve that. And this is one example. Yes, this is an image of a happy girl. Good. If you want to make the girl angry, now you can see everything can be different, right? Similarly, if you make the girl surprised, the background can be different, right? The skirt can be different. How can we do it? How can we do it? If you have this ability, then you can really produce a very nice, fancy picture with a lot of components, right? And you can refine it step by step. You are really an artist, smart artist. We achieve that by making use of kind of causal principles. And to give more illustrations, here you can see some additional examples with OpenAI. We first generate the female image and we try to add mustache, nothing happened. We try to make the girl surprised, a lot of things can be different. Okay? Although we can see they try to make sure images are similar. If you see the color, right? But still a lot of things change. And in contrast, later you see the result produced by our platform. But let me talk about the causal process in the first place. Now you can see we have to align text with images. How? When we say something, basically we try to make ourselves clear. We refer to concepts and relations. So here at this level, we have concepts underlying text, sentences right here, ZT. And then we also have the concept underlying images. And we know that the concepts underlying text are related to the concepts in images, but they are different. For instance, when we say blue, right here it's just a binary variable. It's blue or non-blue, right? But in the images, there are so many different levels of blue. Is that right? So in other words, right here, the concepts underlying images would be more informative. And the concepts in text would be would be more abstract or concise, right? In other words, the textual concept generate the visual concepts. And in this process, additional noise, like the level of blue, can be incorporated. This is the causal process, right? When you try to say something and then produce picture, this is the process. I make myself clear, and then when I really produce a painting, I have to make it more and more informative by introducing some kind of noise, right? Like level of blue. This is the process. Now, by making use of only two constraints, you have identifiability of all the concepts and relations. What assumptions? First of all, we have sparsity constraints right here. Okay? So that, yes, text concepts and image concepts are related. You can see the links, but the links should be as sparse as possible to avoid the actual distortions. Okay? This is one constraint. The other constraint that given the textual concepts, the image concepts are conditionally independent. That's it. Given the two constraints, we have identifiability of the concepts and the relations. Good. This means by making use of constraints, you can allow machines to recover the concepts across text and images together with the relations. Okay? And then you can do controllable generation and controllable editing. Now you can see the result by our method. Yes, we generate the female image and now add mustache because the machine can learn what you mean by mustache and how mustache should be applied. And here you can see, yes, I can just change the facial expression of the girl. Now you can see, yes, the girl became surprised, but nothing else would be changed for that reason. Just because you can allow machine to learn and focus on the specific concepts to make a difference. And here you can see more results. So, and this one is produced by SD3, and this one is produced by DAO3 by OpenAI. Now you can see, yes, you can see a lot of actual distortions, and here similarly, you can see actual distortion. And here we aim to change only the color of the shirt. So it's really controllable. And this is our result. Okay. So now with this illustration, I try to explain that the principle of constraints are so important. Specifically, here I assume the connectivity between textual concepts and visual concepts are sparse right here. If you drop this sparsity constraint, then right here, without the sparse constraints, then you can see actual distortion. Here, I first generate image, astronaut with is riding a horse, and then I try to change the horse to a zebra or unicorn. Without the sparsity constraint, you can see, yes, you can achieve that. But clearly you can see actual distortion. The horse or the animal become different, the gesture is different. And even right here, the orientation can be different. You can see actual distortion. But with sparsity constraint, you just make necessary changes. You can see the animal is almost the same, but now instead of horse, it's a zebra, and now it's a unicorn. And generally speaking, unicorns are smaller. That's why you can see it's smaller, and so on. So constraints are very useful. Basically, it's also known as inductive bias, right? We have to make use of suitable constraints so that machine can really realize and make use of the constraint we make use of in a more powerful way. And finally, you can see I gave this example at the very beginning, right? We can really allow peacock to eat ice cream, and at the same time, we can change anything like. You can just change the color of the ice cream or anything about peacock. So things are controllable. You can do image editing, you can do image refinement in a principled way. But to summarize, first of all, causality is useful for the purpose of making changes, right? In biomedical studies, in biology, psychology, and even in generative AI, you can see we have to care about the causality because you want to make changes to achieve a desired difference. It's controllable. That's why you have to understand the cause-effect relations, and you have to figure out what you can change for that reason. And second of all, you can see that the learning causality is not mysterious. Under some assumptions, which are usually testable, we can read learning causality. We can recover the causal structure together with the hidden variables and relations. And third of all, you can see even generative AI can naturally benefit from causal modeling. Why? Because we try to find the best way to generate images or text, right? Or to make a difference. And right here, basically, we can try to understand the underlying causal process, and then we can try to make use of the causal principle of constraint to avoid actual distortions. And also at the same time, instead of directly understanding and modeling the dependence at the pixel level or at the gene level, we can try to go to a high level to capture the dependence and causal relation and make use of them, right? That's needed. And if you directly capture and make use of the dependence across pixels, it's huge, it's horrible, right? Because you have to make use of very large model to capture all the information. But we know that that's not really the best way or economic way to do so. You can go to the right causal level to capture and make use of the dependence relations. Okay? And in order to do so, we know that, yes, we can use the causal counterfactual changes, and we have a minimal changes to really make sure that things are reflected in image, the text, everything in the right way without introducing actual distortion. And we can learn concepts from multimodal data. And this way, we can even achieve extrapolation. It's not just interpolation. You can really produce new things with guarantees. And at the same time, as I just mentioned, you don't have to capture all the dependent relation at a very low level. Your model is simpler, right? Because of the constraints, and it can become more energy efficient. And finally, you can see, basically, if we can achieve a world where causality is transparent, then everything can be simpler. We can make sure things are controllable. We can make sure we can communicate in a very smooth way. And at the same time, we can try to make sure we don't really waste so much energy and so on. So let's work together to achieve the causally transparent world. Thank you very much.
Thank you, Professor, for giving such a thorough lecture series starting from the basic concept, then causal representation, and then causal generative AI. We have time for a few questions. So,
Thank you so much, sir, for your excellent talk. Regarding assumptions, how you trade up while making strong assumptions or few assumptions